Hi there, warriors. This is Miss Lemons, and today we will be talking about bond energies or bond enthalpies. So before we get started, let's reflect or review the law of conservation of matter, which tells us that matter cannot be created or destroyed, only rearranged. So how is matter conserved? Remember, in a chemical reaction, the bonds of the reactants are broken and the bonds of the products are formed. The atoms rearrange themselves to create new substances. So you can see here in this reaction between C2H6 and Cl2, that's diatomic chlorine or molecular chlorine, we then create C2H5Cl and HCl. Now, we proved the law of conservation of matter in Unit 5. In Unit 7, in chemical reactions, when we were learning how to balance chemical equations, we still have 2 carbons on both sides. We still have 6 hydrogens on both sides, right? But we can also see here in these pictures of the structural formulas of those substances. You can see here that H and Cl were the only things that really switched here in the chemical reaction. The bonds between C and H and Cl and Cl were broken, and then they were reformed between Cl and C and H and Cl to create new substances. So there was only a breaking of bonds, a rearrangement of atoms, and a reforming of bonds. So how does this relate to enthalpy? Well, when those bonds are broken, they require heat energy. We need to put energy into the system to break bonds, right? Think about like if you were to snap a twig, if you were to take those bonds, those pictures of those bonds and snap them like twigs, it takes energy to snap that twig, right? So it takes energy to break bonds. And then when bonds form, energy is then released. So I like to look at these little lightning bolts pointing inwards means that energy is being put into the system, meaning that this is endothermic, and that these pointing outwards, that energy is exiting the system, meaning that this is exothermic. Okay, so breaking bonds absorbs energy. It has a positive delta H, meaning it's endothermic, and then forming bonds releases energy, and that is an exothermic reaction with a negative delta H. And remember, folks, if you have a positive delta H, that means you also have a positive delta T and Q, and the opposite is true for exothermic reactions, or breaking or forming those bonds, releasing that energy, negative delta H, negative delta T, and Q. So how does this relate to actual enthalpy? Now, we can calculate the change in enthalpy. So we know that it takes energy to break bonds, and it creates energy or absorbs energy. Sorry, it takes energy to break bonds, and it releases energy to form those bonds. So we can actually calculate the change in enthalpy that's being put into that reaction or released from those reactions. And we can use that bond chart or this equation. And we're also going to be using this chart of bonds with energies. So this right here, it says delta H equals sigma, or which means sum of all of the bond energies broken. Okay, so this is sum of all of the energies broken, or bonds broken, minus sum of all of the bond energies, or the bonds that have been formed. Okay, so you will be given this equation and you will be given this chart, but we will show you how to use this calculation or this equation and apply it to pictures or structural formulas like you see above. So you can see here that for every bond, there is a specific energy. And you can see that some bonds have higher energy than others. So I think a really nice thing to point out here is like, here is a CC bond, a bond between a carbon and a carbon, and that is 346 joules of energy. Here we have a double bond between 2 carbons, and you can see that has 602 joules of energy, or kilojoules per mole of energy. And then I think we might even have a triple bond somewhere around here. It doesn't look like we have the CC triple bond, but that's okay. You can see that though, by increasing the number of bonds, we've also increased the amount of energy that's required to either break or form that bond, right? So I think it's kind of interesting to kind of think about, why do you think having more bonds, or why triple bonds, release or absorb the most amount of energy? And you have to remember what bonds are made up of. They're made up of those electrons. If there's more electrons, they're going to be more attracted to the nuclei of those atoms. It's going to be harder to break, right? So more bonds means it's going to be more difficult to break or to form. It takes more energy. It makes more energy, one of those two. So we will get into practice, but that concludes the video for today.